Hi everyone, welcome back to another astronomy presentation. Today we will be discussing the night sky. So if you're following along in the famous OpenStax online book, this presentation will go along with pages 31 through 41 of the 2017 edition of that book. So some motivation. By about 20,000 years ago, people who we now call the Polynesians had colonized New Guinea and the Philippines. But it took them a bit longer, until about 800 BC, before they had colonized the various islands in the equatorial and South Pacific, the areas that we now call Polynesia. And that's because they were able to use celestial navigation, using the sun, moon, and stars. If you've seen Disney's Moana, you've seen some of that. But once they ended up crossing the equator, that became a bit difficult for them. In fact, it wasn't until about the year 8600, that is 600 AD, that the Polynesians had actually finished colonizing Hawaii. In other words, the so-called native Hawaiians are actually pretty recent inhabitants of what had previously been an uninhabited island about 1400 years ago. So they achieved their success, as I mentioned, from island hopping and using the stars and ocean currents, but they had a lot of trouble in certain areas because they ended up coming across new stars as they ended up going to very new latitudes. So, how can we make use of the stars for navigation and, for that matter, just knowing when things are going to rise and set in the night sky? So it's often useful to think of the sky as a great dome over our heads, the so-called celestial sphere, and the horizon is where that dome meets the Earth. We always think of the horizon as simply where the ground meets the sky. Well, the same thing works here. Another vocabulary term is the zenith. The zenith marks the point that is directly overhead. And as Earth turns, that dome turns over our heads, and it appears as if the sky is a large hollow sphere centered on Earth, kind of like this. Now, notice that as Earth rotates and new stars come into view, different stars are going to go by the zenith. The only exception to that would be if you happen to be living at the north or south geographic poles, and in that case, nothing new will occur over the zenith. So, what follows is you're going to have a big assortment of facts, information, and stuff like that. You should generally be familiar with procedures, certain useful information that I will try to make clear, and other important facts. And a lot of vocabulary terms are also going to be important. In fact, this is one of the most vocabulary-laden presentations of the entire course. So just bear that in mind, bear with me. If you can get through this, then you'll probably be fine in terms of vocabulary this year. So, a degree. You know about a degree. It's 1/360th of a circle. So we divide a circle into 360 degrees. And then navigators, geographers, and for that matter, astronomers found it useful to subdivide a degree into 60 smaller parts, which we call arc minutes or minutes of arc. And for very precise angular measurements, it becomes useful to divide an arc minute itself into 60 smaller parts. So we call those arc seconds, or seconds of arc, or just seconds. So that means that 1 degree is 3,600 seconds, or 3,600 arc seconds. To get an idea of what a small unit of angular size that is, a penny seen from 2.2 miles away would have an angular diameter of 1 arc second. Same thing with a quarter seen from about 5 kilometers away. So it's a very small unit of angular measure. The sun and moon are about 30 arc minutes in angular diameter. It's an interesting coincidence that during the time of basically early human civilization, the sun and moon happen to have the same angular diameter in the sky so that we can celebrate things like total solar eclipses and stuff like that. If the moon was much closer to us, it would easily cover up the sun. So yeah, you'd have more eclipses, but they wouldn't be as spectacular in either appearance or occurrence. And if it was a bit smaller, then the moon would never be able to block out the sun's disk, and the best you would be able to have would be annular eclipses. We're going to talk about those in a future discussion relatively soon in this unit. Other units of angular size. Well, if you hold your index finger at arm's length, that's about 1 degree across. That's about 1 degree across. Your closed fist held at arm's length is 10 degrees, and your outstretched hand held at arm's length is about 20 degrees across. So that way you can kind of see how this goes. So your outstretched hand being 20 degrees across, your index finger itself being 1 degree, closed fist is 10 degrees across. Also, the angular distance between the stars Dubhe and Merak, those being the pointer stars in the Big Dipper part of Ursa Major, that's 5 degrees. So that's also something that's kind of good to know when you're trying to just navigate the night sky by eye. The height of a star above the horizon is called its altitude. We've discussed this in other contexts before, but the height of a star above the horizon is called its altitude. But the direction of a star measured from geographic north is called its azimuth. For example, due east is going to have an azimuth of 90 degrees. Now, in terms of altitude, that's where the whole closed fist at arm's length thing kind of becomes very useful. If somebody tells you that at a certain time of night a planet is going to be 20 degrees above the southern horizon, well, then you just look kind of toward the south with your closed fist at arm's length, the bottom of it at the horizon, the top of it marks 10 degrees, put your other fist on top of that, well, the top of that's going to mark 20 degrees. So then you look around and hopefully you see the planet, unless they're lying to you. So I should also mention, when we talk about azimuth, that we're talking about azimuth from true geographic north, not necessarily what a magnetic compass would tell you, because Earth's magnetic pole is not in the same location as its geographic pole. Even more, Earth's magnetic pole is moving over time. So that means, yeah, you cannot trust a magnetic compass in general. So some old maps have corrections to those types of things. For example, where we are in Northern Virginia at the time this map was made, a typical magnetic compass would have told you that north is 10 degrees different from where north actually is. Nowadays it's actually a little bit better because of how the shifting of the magnetic North Pole has occurred, and now we're probably more like about 5 degrees or something like that, but it's still off. The North Star, Polaris, is much closer to true geographic north for most people than a magnetic compass would indicate for the direction of true north. Though that is only true during our lifetimes. If you were to have looked at Polaris 1500 years ago, it would not have been all that close to true north, or at least not all that much closer than a typical magnetic compass would lead you to. So, with altitude and azimuth, we use units of degrees, minutes, and seconds for our angular measurements. For stuff that you can just eyeball, usually degrees, and every once in a while degrees and minutes is good enough. But if you're trying to use a telescope to find an object, you would need to use degrees, minutes, and seconds, especially if it's a faint, small object. Now, the celestial sphere. So we've mentioned it before. It's this imaginary sphere onto which you can imagine the projections of the stars and the planets and the sun and the moon onto a just very big sphere centered upon Earth. And the idea is that as Earth rotates, our view of the celestial sphere ends up changing, except if something happens to be at the North Celestial Pole, which is a point on the celestial sphere directly above Earth's North Pole, or the South Celestial Pole. Though it turns out there aren't really any bright things near the South Celestial Pole, except every once in a while a satellite, in which case it wouldn't really matter anyway because it's not going to stay there for any more than a few seconds. So, the celestial equator is the set of all of the points onto the celestial sphere that are directly above Earth's equator. So, in this case, the celestial equator is this kind of curved, what we call a great circle over here. A great circle is something that you would get just by going, quote, straight on a sphere. And you would eventually come back to where you started, and you would traverse a path called a great circle. Well, the celestial equator is a great circle, because Earth's equator is a great circle. And all lines of longitude are also great circles. We're going to come back to that soon. Lines of latitude, however, are not, so I want to warn you about that. So, stars move from east to west because of the fact that Earth is rotating from west to east. So, going back to this area, well, Earth is rotating from west to east, so that if we just keep ourselves focused and pretend that we stay on the top as Earth rotates, that would mean that from our perspective, the celestial sphere rotates from east to west. So we view the sun rising in the east and setting in the west, generally speaking, or an eastish direction and setting in a westish direction, though it only rises exactly east and sets exactly west during the vernal and autumnal equinoxes. And it just so happens that the date in which I am making this video is the autumnal equinox. So, nice coincidence there. So, we mentioned the north and south celestial poles, those points directly over Earth's true north and south poles, and the celestial equator. There's also another important great sphere, a great circle, and that is the meridian. The meridian is a line from due north to due south that passes through the zenith. It's quite important in terms of speaking in navigation and in observational astronomy. In fact, our terms AM and PM come from that term. AM means antemeridian, before the sun crosses the meridian. PM means post-meridian, after the sun crosses the meridian. Now, there are some stars that are located very close to a celestial pole. In the northern hemisphere, we think of the North Celestial Pole. Obviously, Polaris is an example of such a star. Polaris is very close to the North Celestial Pole. And if you're at, say, mid-northern latitudes, you're going to find a number of other stars that are close enough to the North Celestial Pole such that they are always above the horizon. They never rise or set. They go higher and lower, but they never disappear below the horizon. We call those stars circumpolar stars. Circumpolar stars. So those are stars that as Earth rotates, they simply stay above the horizon. So in this case, these stars that you see in these tracks in this time exposure photograph are all circumpolar stars. And do you think you can find Polaris in this picture? Sure you can. It's the nice bright one close to the North Celestial Pole. So, as I'll mention later, Polaris is not the brightest star in the night sky, but it's a reasonably bright star that is conveniently close to the North Celestial Pole. So, quick examples. If you are at the North Pole, well, the North Celestial Pole is the point directly above Earth's north geographic pole on the celestial sphere. Well, that would mean that the altitude of the North Celestial Pole is 90 degrees if you are standing at the North Pole and sharing a latte with the polar bears. So, in that case, any stars that happen to be above the horizon at that location are going to be circumpolar, because they're just going to be rotating around, or appearing to rotate around the North Celestial Pole as Earth actually rotates. However, if you were to fly 10 degrees south of the North Pole, then the North Celestial Pole's altitude would be 80 degrees. It wouldn't be directly overhead anymore, because by flying 10 degrees south, you have also gone 10 degrees over the horizon. You have curved your location with respect to the North Celestial Pole by 10 degrees. Remember, Earth is a sphere. So in that case, the North Celestial Pole's altitude would be 80 degrees. So, you could say that any star that is within 80 degrees of the North Celestial Pole must be circumpolar, because if it's within 80 degrees, that means the worst that could ever happen to it is, at least from our point of view, is that it would kind of skim the northern horizon. Well, what that means is that the altitude of the North Celestial Pole is always equal to your latitude. There's a nice anagram there. You rearrange the letters of the word altitude and you can get latitude. In fact, all you have to do is just switch the first A and L. So it's not that hard. So all stars within that latitude amount of the North Celestial Pole will be circumpolar. So you can see this very nicely in Stellarium with a continuous change in latitude. When you change your location, you can see the change in the North Celestial Pole. So in Northern Virginia, our latitude is about 39 degrees north. So what that means is that the North Celestial Pole is 39 degrees above the northern horizon, meaning that all stars within 39 degrees of that North Celestial Pole are going to be circumpolar stars. However, If you're at the equator, that would mean that the North Celestial Pole, and the South Celestial Pole for that matter, would both be at the horizon. So there would be no circumpolar stars at the equator. Okay, I've kind of lied to you a little bit there. There are some interesting optical effects due to Earth's atmosphere that make it so that stars that are close to the horizon appear to be a little bit farther above the horizon than you would think. So actually, stars that are at the North Celestial Pole would appear a little bit above the horizon at the equator. But without the atmosphere, that wouldn't be a thing. So yeah, fine, the Polaris is, I'm sure, still circumpolar at the equator, but only because of that cool optical effect of the light refraction due to Earth's atmosphere, changing column depth, changing density, that sort of thing, as the light goes onto its track to us. Anyway, so similarly, as I just mentioned, at intermediate latitude, you have a lot of stars that are circumpolar, and they're the ones that are closer to the North Celestial Pole. Now, there is also a trade-off. At the North Pole, standing at the North Pole, yeah, all the stars are circumpolar. But guess what? Any stars that aren't above the horizon are stars that you will never see above the horizon. You cannot see any southern stars at all from the North Pole. But as you go farther and farther south, you can see more and more southern stars. And the farther south you go, the more southern stars you're able to see, and the higher they will get above the horizon, such that by the time you get to the equator, you can see any star at some point during the night. Or, depending on the time of year, you might have to wait a few months if that's a star that would come up during the day. So, as we mentioned, Polaris is conveniently close to the North Celestial Pole right now. That is not always true for reasons that we will get to later on. And in the southern hemisphere, unfortunately, they do not have any bright stars near the South Celestial Pole. Like the brightest star that's really somewhat visible to the unaided eye that's close to the South Celestial Pole is Sigma Octans, which is something like the 3,000th brightest star in the night sky, whoopee. So instead, you need to use some other method to find the South Celestial Pole. Well, there is another method. There is a constellation called Crux, which is often called the Southern Cross, that points approximately toward the South Celestial Pole. But it's not near the South Celestial Pole, so what you have to do is you have to wait for a while Earth rotates and kind of draw a couple of baselines or a couple of imaginary lines, and where those cross each other, that's going to be where the South Celestial Pole is. Unfortunately, that is not necessarily always convenient for navigation. You don't exactly have trees in the middle of the ocean by which you can use as reference points for drawing these lines over the course of hours. So as I mentioned before, there is this misconception that the North Star is the brightest star in the nighttime sky. In fact, Polaris is only about the 45th brightest star in the night sky. And, as it turns out, due to the effects of precession of Earth's axis of rotation, again, we're going to talk about that later, in about 14,000 years, Vega, the 5th brightest nighttime star, actually will be the North Star, so that will be very convenient. Just so you know, the brightest star in the nighttime sky is called Sirius. It's in the constellation Canis Major, the big dog. It's from mid-northern latitudes. It's visible during the early evening in late winter and early spring. And if you want to see it during the summer and early fall, then you need to get up early enough in the morning before the sun starts to blot out the stars. So here again is a nice time exposure photograph showing star trails and Polaris near the North Celestial Pole. And yeah, notice Polaris doesn't really move much. Polaris is less than a degree away from the North Celestial Pole. Now, more about the celestial sphere. Well, to find due north, you can drop straight down from the North Celestial Pole to the horizon, and the celestial equator meets the horizon at due west and due east. That's going to be true anywhere around the globe. No matter where you are, the celestial equator is always going to meet the horizon at due west and due east. In fact, that's the thing about the equinoxes, the vernal equinox in spring and the autumnal equinox in the fall, when the sun is actually crossing the celestial equator, which is why it rises due east and sets due west only on those 2 days. Now, talking about latitude and longitude, we need to do this a little bit so that we can talk about celestial coordinates, because as you have figured out already, altitude and azimuth are not very convenient coordinates because stars' altitudes and azimuths always change due to Earth's rotation. The only time that that won't change is if you're either looking at Polaris, and even that changes a little bit, or if you happen to be at the North Pole, and in that case, the azimuth will change, but the altitude will not. So, latitude is your north-south position on Earth. And the equator is defined, as you know, to have a latitude of 0 degrees. North Pole is at 90 degrees north, the South Pole is at 90 degrees south. Or you could say negative 90 degrees north. Same thing. Keep that in mind. Longitude is your east-west position on Earth. For example, an arbitrary point, the prime meridian in Greenwich, England, marks a longitude of 0 degrees, and that's what this last picture was. This is the post office in Greenwich, England, and you can see the line here marking where the prime meridian is, and that denotes a longitude of 0. They could have made it anywhere. They could have made it Oakton, Virginia, or something like that, but they decided not to. Oakton, Virginia didn't exist at the time that they decided this. So arbitrarily, it's at Greenwich, England. So, for example, one of the biggest observatories in Virginia, in fact, the biggest refracting telescope observatory in Virginia, is the Leander McCormick Observatory on UVA's campus, up so-called Mount Jefferson, but usually just called Observatory Hill. Its altitude, 264 meters above sea level. Longitude, 78 degrees, 31 minutes, and 19.8 seconds west. And latitude, 38 degrees, 1 minute, and 58.2 arc seconds north for the latitude. If you're trying to translate these into GPS coordinates, you might need to turn these into decimals, or if you already have them as decimals, you might need to convert it back. It just depends what type of device you are using or what type of app you are using. Now, why is this important for us? So, if you find a place on Earth, it's at a fixed longitude and latitude. However, the stars change their locations in the night sky as Earth rotates. So it becomes convenient to apply a very similar, not identical, but very similar type of coordinate system for the stars. It can't be identical because as Earth rotates, the longitude is under different points in the celestial sphere. However, the latitude is not. So, declination coordinates, the north-south position of a star on the celestial sphere, is its declination. It's exactly like latitude. In other words, if you are at a latitude of 40 degrees north, then any star that has a declination of plus 40 degrees will, at some point over the course of a day, pass through the zenith. In other words, the declination is a fixed declination curve is going to be the set of all points that are directly above that line of latitude on Earth. Can you think of an example of that? We've already encountered it. Yeah, the celestial equator. The celestial equator is a line of declination. What declination coordinate would it have? How about 0 degrees, just like Earth's equator? But with declination, instead of saying north and south, we say positive or negative. So if something is a southern star, it's going to have a negative declination. Something is a northern star, it's going to have a positive declination. Okay, what about right ascension? Right ascension is kind of like longitude. It's not exactly like longitude, though, because, again, Earth rotates. And as Earth rotates, the stars in the night sky appear to move. Well, we want to give the stars fixed coordinates, so that if anybody ever says, go to Vega with the telescope, then you simply type in the celestial coordinates for Vega, and the telescope slews to that location and points toward Vega, and you end up getting your eyes burnt out because it's a very bright star. So, well, if it's a small telescope, that won't happen. But anyway, something to keep in mind. Yeah, declination is exactly like latitude, but right ascension is only kind of like longitude. So, for example, with Vega, Vega has a declination of about 38 3/4 degrees. I say 3/4 because 44 arc minutes. There are 60 arc minutes in a degree. 44 is about 3/4 of 60. So that's, well, if you're living in Northern Virginia, that's pretty close to your latitude, which means that at the right time of night, Vega passes very, very close to the zenith, which is kind of nice. Its right ascension is 18 hours and 35 minutes. Yeah, those are funny units for right ascension. We're not talking about degrees here. Why do you think we're talking about hours and minutes? Yeah, because we want to talk about it in terms of time, in terms of when it's going to rise. Well, when is it going to rise? Does that mean it's going to rise at 6:35 p.m. every single day? Well, I would hope not, because after all, Earth is revolving around the sun, so that would end up changing things. So instead, it's relative to something. It's relative to something. What's it relative to? So that's how it's. Here's the idea. Just as I mentioned, declination is like latitude, and it determines visibility. Right ascension is like longitude, and that means that 18 hours and 35 minutes, that means that if you know of something that rises at a certain time, if it has a right ascension of 0, then Vega would rise 18 hours and 35 minutes after that object, assuming that both objects are relatively close to the celestial equator. We'll get into those types of situations relatively soon. But let's talk a little bit more about declination first. Figuring out an object's declination will allow you to determine whether or not it is visible from your latitude. Because remember our discussion about how, okay, anything that's within 10 degrees of the North Celestial Pole is going to be circumpolar for anybody at a latitude of 10 degrees. And anybody at a latitude of 40 degrees for us, well, that means the North Celestial Pole is 40 degrees above the horizon. So anything that's within 40 degrees of the North Celestial Pole will be circumpolar. Well, it's a similar type of logic with declination. So here's the idea. If your latitude differs from a particular star's declination by more than 90 degrees, that means that that star, or whatever it is forever doomed to remain below your horizon. Because, after all, I mean, your zenith has a declination equal to your latitude. Your zenith has a declination equal to your latitude. That's the rule. I mean, that's how declination is defined. So, since your zenith has a declination equal to your latitude, then anything that is more than 90 degrees away from your zenith can never come above the horizon, at least in terms of declination. Now, if it's 90 degrees away from the zenith, but it has the same declination, well, okay, then you just wait 6 hours and then it'll be at the zenith. Now, I'm talking about the declination is talking about in terms of what can ever be at your zenith. So, since we're talking about, say, you're at a latitude of 40 degrees, that means your zenith is at a declination of 40 degrees. Well, any star that passes through the zenith has a declination of 40 degrees. So just wait 24 hours, and any star that goes through that zenith, that is the set of all the stars that has a declination of 40 degrees. Well, if during that time there were any stars that had declinations of more than 90 degrees away from 40 degrees, and the only way that's possible is to have a declination of 90 degrees less than 40 degrees, that is, a declination of negative 50 degrees or less, that would mean that even at its peak altitude, it's still not above the horizon. It's still not above the horizon. So for any star that would have a declination of, say, negative 52 degrees or negative 55 degrees, that means it is not going to be visible from a latitude of 40 degrees or more. So if you're farther south, if you're in the northern hemisphere, will make it more easily visible, and farther north in the southern hemisphere would make something more easily visible. So, consider the star Polaris. Its declination is, at least translating to a decimal, about 89 and a quarter degrees. So it's visible at all latitudes farther north than minus 3/4 of a degree. In other words, all latitudes farther north than 3/4 of a degree south of the equator. So in other words, I said, okay, I know that people at a latitude of 89 and a quarter degree would see it go directly north, directly overhead, at some point during the night. So imagine what it would look like where I would have to go so that it would be at the horizon. Well, if it's directly overhead and I'm at a latitude of 89 and a quarter degrees north, well, for it to be at the horizon, I would need to go south by 90 degrees because the horizon is 90 degrees below the zenith. So rotating myself south by 90 degrees, by walking 90 degrees south or something, then that point would be on the horizon. Well, what's 90 degrees south of 89 and a quarter degrees north? That's right, 89 and a quarter minus 90 is negative 3/4 of a degree. So anybody who is south of 3/4 of a degree from the equator, south of the equator that is, will never see Polaris, at least if you ignore those cool refracting effects of Earth's atmosphere. What about the star Alpha Centauri? In which latitudes would this star be visible? Well, let's see now. Alpha Centauri has a declination of minus 60.84 degrees. And for now, we'll just call that minus 61 degrees and then do the math from there. Well, if I want to even have a prayer of seeing Alpha Centauri, I need to make sure that I am within 90 degrees of that negative 61 degrees. In other words, even at its peak, even at the best of circumstances, that would mean that Alpha Centauri is directly overhead at a certain latitude. Well, that latitude where it would be directly overhead in the best of circumstances, in other words, when Earth is rotated just right, would be at a latitude of 61 degrees south, or minus 61 degrees. Well, how far north can I go and still see this? Well, how about if I'm at negative 61 degrees latitude, if I go north 1 degree, well, then it's 1 degree from the zenith. If I go north 10 degrees, it's 10 degrees from the zenith. If I go north 90 degrees, then it's 90 degrees from the zenith. That's called the horizon. So what's 90 degrees north of negative 61? Well, negative 61 plus 90 is positive 29 degrees. And since it was actually 16.16 degrees more than negative 61, then just add 0.16 degrees to that 29 that we got, and you say, okay, if you're at a latitude of 29.16 degrees north, then that star, Alpha Centauri, the closest star system to our sun, will be at the horizon. If you actually want to see it well, you need to go south of that latitude. Well, Orlando is south of that latitude, so that's nice. So yeah, in southern Florida, you can see the star. Now, try another example, and maybe pause the video after we're done saying what the example is. Consider the globular cluster Omega Centauri with a declination of about negative 47.5 degrees. Is this cluster visible from Oakton High School at a latitude of 39 degrees north? And if so, what's its maximum altitude above the horizon? And if not, what's its minimum altitude below the horizon in the best of circumstances? So pause the video while you make this calculation. And if you have unpaused the video, or if you've finished making the calculation, let's check your work now. Well, the question is Oakton High School within 90 degrees of that declination? In other words, is it within 90 degrees of that latitude? In other words, remember, declination means that it can be at the zenith for that latitude at some point during the day or night. Well, you need to say, okay, negative 47.5 degrees plus 90 degrees, that turns out to be 42.5 degrees. Is 42.5 degrees greater than our latitude? Well, our latitude is 39 degrees. And since our latitude is 39 degrees, and 42.5 degrees is 3.5 degrees more than our latitude, that means that at the best circumstances, this globular cluster is 3.5 degrees above our horizon. Yeah, Omega Centauri is kind of an amazing object. We used to think of it as a globular cluster. Now we recognize that it's probably the core of a galaxy that the Milky Way absorbed and stripped all the stars away from that galaxy except for the stars around the core. So that's kind of cool. Okay, so declination and circumpolar stars. Well, that's something we've already kind of looked at to some extent. So, for example, observers at 40 degrees will observe stars that at 60 degrees declination to be circumpolar. Why? Well, because observers at 40 degrees would note that any star that is within 40 degrees of the North Celestial Pole is circumpolar. Well, okay, what does that mean? The North Celestial Pole, remember the little mnemonic there, the North Celestial Pole's latitude is always equal to an altitude above your horizon to your latitude. Sorry, I should say the altitude of the North Celestial Pole above the horizon is always equal to your latitude. So, any stars within 40 degrees of that are going to be circumpolar. Well, what's the declination of the North Celestial Pole? Hopefully you remember that the declination of the North Celestial Pole is 90 degrees. In other words, the latitude of the North Pole. So anything within, at our latitude, 40 degrees of a declination of 90 degrees would be a circumpolar star. That is, anything with a declination greater than 50 degrees. So, stars that have declinations of 60 degrees are definitely circumpolar. So, it's kind of a complementary angle type of thing. Let's end this video with a few more examples of this, and then we'll save our elaboration of right ascension for the next video. So, let's say you're in Oakton, Virginia, at your latitude of 39 degrees. What would be declinations of circumpolar stars? Well, circumpolar stars would be all stars with declinations within 39 degrees of the North Celestial Pole, which is at a declination of 90 degrees. So, well, within 39 degrees of 90 degrees would be anything with a declination of 51 degrees or more. So that would be circumpolar stars. What about Fairbanks, Alaska, with a latitude of 65 degrees north? Well, 65 degrees is 25 degrees away from 90 degrees. So that would mean all stars with declinations of 25 degrees or more are circumpolar stars. Well, guess what? There are more stars with declinations greater than 25 degrees than there are stars with declinations greater than 51 degrees. Because after all, the maximum possible declination is 90 degrees. That's the North Celestial Pole. So the farther north you go, the more stars are circumpolar stars. But of course, the farther north you go, the fewer southern stars you can actually see. So that's actually most northern hemisphere stars in this case. What if you're in Sydney, Australia, with a latitude of 34 degrees south? That is negative 34 degrees. Well, which declinations there are circumpolar stars? Well, that means that, remember, think about the complementary angle there. The complementary angle of 34 degrees would be 56 degrees. That would mean any stars with declinations of minus 56 degrees or less, that is more negative than negative 56 degrees, will be circumpolar. So, next time we will talk about right ascension. Today we've talked a lot about declination. We introduced the concepts of right ascension and declination, as well as celestial coordinates in general. So in the next video, we will discuss right ascension in more detail. Until then, thank you for watching.